Hello, everyone. Thank you for coming to Robotics Seminar. So today we have our very own Dr. Wen Sun, who is in computer science. His work focuses on reinforcement learning, which will be the topic of his talk today. And prior to Cornell, he received his PhD from the Robotics Institute at Carnegie Mellon. So obviously relevant to what we're all interested in. So Dr. Sun, take it away.
Thanks. Hello, everyone. So I'm going to talk about model-based reinforcement learning and control today. And I will talk about things from the information theoretical considerations of model-based RL to algorithms that we can actually implement and test. Okay, so reinforcement learning is a very popular research area these days. And we have seen that people use reinforcement learning techniques to solve these challenging problems, including this Asian board game Go and this multi-agent video games, Dota. So basically, we have seen the trend that if you have enough computation resources, right, and if you have enough samples, you can have basically infinite samples in these simulations and games, right? So reinforcement learning is really effective in the sense that you can really learn something that is actually outperform human level, right? Even the experts in these games. So if you look into the reinforcement learning literature, so there are basically two families of algorithms. So one is model-based and one is model-free, right? So they differ in terms of the effort you use in terms of modeling the dynamics. So in this first example, in this motion planning problem, for instance, we have perfect dynamics, right? We have perfect 3D scan of the patient's head, and we can do very precise motion planning in order to solve some task. But when we get to situations where we're trying to drive this car at a high speed on a tough terrain, things get a little bit difficult, right? So we have this tough terrain, and sometimes the car just drift around, sometimes the car jump around. It's really hard for us to write down the dynamics, right? We know some part of the dynamics of the car, but it's really hard for us to write down, precise equations. So typically what people would do is to use data-driven approach. Okay, so you collect a bunch of data, you're trying to learn something, p hat, an approximator that approximates the true transition dynamics that corresponding to the car driving at this particular speed on this particular track. And another approach is model-free, where you don't even spend any effort or time on trying to model the transition dynamics. All you do is learn some function that takes this image as input and output what the control input is, output the control. Okay? And your goal is to directly optimize the reward of this game. Okay? So there's no effort of modeling, how the game is involved, right? All you care is to learn the control, closed loop control policy that solves this game. Okay, so this is called model free. And here we're gonna focus on this model-based RL setting. Okay, so this is the roadmap for today. We're gonna start from some information theoretical result where we're gonna look into a comparison between model-based learning versus model-free learning. And then we're gonna move to a sort of specialized family of models, which we call Kernelized Nonlinear Regulator, where we will see how we can do learning to control in an online learning fashion. And then last, we will consider sort of this same to real setting. So here, real, I have quote on here because we're not really doing real robotics here. So basically, we're trying to see if we can do sort of policy adaptation from a environment to a different environment. Okay, so a policy that is trained on simulation and how we can adapt it to a different testing environment as quick as possible. And we're gonna do it in a model-based fashion. And we're pretty much gonna stay inside this framework, which is Markov decision process. Okay, so we have a learning agent and we have an environment. And in this talk, we're gonna use this notation pi to represent this closed loop policy. Okay, so a policy that takes the state of the environment, which represents the current status of the environment, and then outputs an action. Okay, and once the environment receives the action, it will evolve accordingly. It will send this one-step reward back to the agent, and it will also generate the next state, x prime, based on the underlying unknown Markovian transition. Okay? And then this loop goes on for h many steps, and our goal here is to find this closed loop policy that maximizes the expected total reward across this h many steps. Okay, so here the expectation is taken with respect to the randomness of the environment and the randomness of the policy. Right? Our policy could be a randomized policy in this case. Okay, so model-based learning is indeed not super straightforward. Okay, so let's consider a very naive approach here, right? So what I'm gonna do is I'm just gonna act randomly to collect a lot of data. And then we're gonna use our favorite deep learning tools to fit a model, right? And we probably hope that we can fit a global model, and then we can use the model to do, control or planning. But this is kind of hopeless, right? Let's look at this simple example where my goal is to trying to train this humanoid robot to run faster, run as fast as possible, right? If I act randomly in this simulation, all the robot is doing is basically just falling down, right? In other words, I can collect infinite data inside this simulation. I can use whatever deep learning model that we want, no matter how deep it is. It doesn't really mean that the combination of these two gives us a useful model, right? So all the data you collected is about this robot falling down, and we have no idea how to model the dynamics of the robot when it's running at a particular speed or jumping at a particular height or something, right? So this is indeed challenging. If we want to learn a model that models the robot running at a particular speed, we'd better to figure out how to collect the data, right? Okay, so the setup of this talk. So we're going to start from a very abstract model. Okay, so let's assume that we have some ground truth transition model P star, which is unknown, right? So we're going to use a set of function approximators to approximate this unknown transition. Okay, so each function approximator is basically a mapping that maps from state action pair to the distribution over the next state. Okay, so this is the same format as the ground truth transition model. This is the Markovian transition model. And we're going to assume that our function class, is rich enough so that there exists one function approximator in the function class is good enough to approximate the true P star. Okay, and then for this information theoretical consideration, we're going to assume that we have an access to an optimal planner, which basically says that it takes a transition model, a Markovian transition model as input, and takes a reward function as input, and try to output a policy that optimizes the reward function under the given transition model P. Okay, so in this talk, I'm going to overload the term reward and a cost. Okay, when I see reward, we are trying to maximize the reward. When I see cost, we are basically trying to minimize the cost.
Okay, can I ask a question?
Yes.
You said the reward is after a single action, but really the reward you're interested in is something that's maybe way later in time,
yeah,
and can't be determined. So are you assuming that somehow you have a rollout policy and you evaluate the single action by the current rollout policy, or are you only considering a subset of problems, or only cumulative costs, or what? You understand my question?
I guess so. Let me repeat your question, see if I understand. You're asking that we interested in optimizing the long-term reward, right? Which is the sum of the total reward.
Well, it might not even be a sum. It might be some kind of net performance.
Yeah.
Like,
so
does it like for example, not falling down, or total distance traveled, or
yeah. Okay, so I think so this is a good question. So in this talk we will not be able to capture the the setting except the additive model.
You can only do additive model.
We can only do additive model for this talk, but you can imagine the setting where, for instance, you just you have a reward everywhere at the very beginning, and you get a reward at the end of the trajectory that quantifies how good that trajectory is, right? So you have 0, 0, 0, 0 everywhere except one big reward at the end.
So you could model,
capitalize.
Except for that you don't have any, you have no data, you have nothing to learn from it until you get to the end.
Yeah, so that's the harder problem, right? So that's why we need to do exploration.
Okay, maybe just translate. I think I might be relatively familiar with this problem, so maybe just translate the discussion to the other people, and then I'll let it go.
Okay, yeah.
Just tell people what the conversation we had, and then
yeah.
Go on.
Okay. Thanks. Okay, yeah, feel free to ask questions and turn on your video and ask questions. I'm happy to answer.
So I have a continuing question for Professor Andy. So is it because of the Markov decision process, which makes the reward as just accumulated as a single time step?
I mean, I think you should ask him. I think he understands the question in context, and let him answer in his language. Are you asking me? When should answer, I think.
Oh, yeah. Can you repeat the question again?
So the Professor Andy Rina, like he asked about is there a reward after like episode ends or after several time steps? And you said they are always break down to the like every single reward for each single time step. So I was like wondering if that limitation comes from the assumption of like Markov decision process of the reinforcement learning, or
Not really, right? So, Markovian assumption is more on the transition dynamics. So what basically it says that, my next state is only going to depend on the state and action at the current time step, right? So this has nothing to do with reward. So indeed, you can design reward that, is a complicated black box function, maybe on the entire trajectory. That's totally possible. And there are algorithms that can deal with that. For instance, like policy gradient method, right? You can just do policy gradient using that access to that black box reward function along the entire trajectory. But in this talk, we will sort of restrict it to the setting where every time step you have a reward, and we're interested in the sum of the total reward across the trajectory. But one example you could think about this as this is sparse reward, where you have reward everywhere. All the way at the end of the trajectory, you get a reward. Either you succeed or not. Okay, so this should be considered as a very challenging problem because you don't get any reward along the way. So you don't know how to do credit assignment, right? So you take a bad action at the very beginning, but the consequences you will see probably at the end of the trajectory. And when you're looking back, you don't know which action to blame because you don't know which action actually caused you to fail at the end, right? So that's actually the challenging problem. Yeah. Andy,
I don't know if this fits your pattern or not, but you could have a current, in your optimization, you have a current policy, and then you could roll that out at every time step, and then you have an instantaneous reward for how you do at that time step, assuming you use your current policy. Does that fit your world?
That fits my world, yeah.
So that's a way. So that's a way of accommodating, turning everything into one step reward. Is use the policy, the rollout policy to figure out the net reward.
Yeah. So this is exactly similar to something like a policy gradient people use. So you just execute your stochastic policy, you get a trajectory, you do likelihood sort of weighting based on the reward of the trajectory, and then you adapt, your policy. Yeah. Okay. So the first result that I want to quickly mention is in terms of this comparison, in terms of sample complexity between model-based learning and model-free RL, and with this general function approximation setting. Okay, so we're not assuming anything about the underlying discreteness or continuousness of the Markov decision process. So the result that we had a while ago is basically there exist MDPs where in order to learn a near optimal policy, there exists a model-based reinforcement learning algorithm that only going to span time sample polynomially with respect to the relevant parameters of the model. And for any model-free algorithm, note this is a family of model-free algorithm, not a single model-free algorithm. It needs to span time samples at least exponential with respect to the horizon. Okay, so horizon, remember we consider the problem where we have H many steps. Okay, and this family of model-free algorithms, including the traditional ones like Q-learning and policy gradient methods. Okay, so this is really sort of the first separation bound between a model-based learning and a model-free learning in terms of the sample complexity. Okay, in this general setting where we use function approximation to model our transition dynamics. And this kind of motivates why we want to study model-based RL in the rest of the talk. And indeed, along that separation result, we had a very unified general algorithm that is capable of solving pretty much every MDP structure that people proposed in the literature that can be solved efficiently in terms of sample complexity. Okay, so we have this unified algorithm that is capable of solving this small discrete MDPs, this continuous control problem LQR, and this Lipschitz continuous MDPs and some factored MDPs. So basically every special structure MDP people proposed in the reinforcement learning community that is solvable in polynomial time, this unified algorithm is solvable in the same amount of time as well. So that seems nice, But one drawback of this algorithm is that this is not a computationally efficient.
So can you just refresh what MDP is?
MDP is Markov decision process.
Okay, sorry.
Yeah. So the algorithm is not computationally efficient. Okay, so I want to emphasize the difference between sample and computation. So the algorithm is sample efficient. Okay, so in other words, you just collect a polynomial number of samples. But once you collect some samples, some computation that is happening inside this algorithm requires you to solve some NP-hard problem. Okay, so that's why I say this is not computationally efficient. In a sense that this is information theoretically efficient in terms of number of samples, but computationally, we don't know how to make it efficient. Okay? So this basically means that this is an algorithm that ideally is efficient in sample, but we cannot really implement in practice, right? Unless we have maybe infinite computation power, which we don't. Okay, so I'm spending pretty much 1.5 years trying to sort of come up a computation efficient and also statistically efficient algorithm at this general level, but I kind of failed. So what we did is that let's take a step back. Let's probably look at a more restricted model. Okay, so this is the model that we call it kernelized nonlinear regulator. I will dive into the model in the next slide. And what are we going to do here is to, again, get provable guarantees in terms of the learning to control setting. And we also want to get some implementable algorithm, right? And again, we're going to assume access to black box optimal planner or control. Okay, so this is a very simple model. Okay, so all we're doing is to try to model this discrete time dynamics. Okay, so I have state action at current time step t, and this nonlinear function f star takes them as input, and together with the additive Gaussian noise, it outputs the next state. Okay, so this is discrete time dynamics. And what are we going to assume is that this f star can be modeled by kernel or Gaussian process. Okay, so there's some previous work which is called empirical, basically was kind of the first paper that trying to use Gaussian process to model these dynamics and then using control methods on the learned dynamics to control the robot or the simulation.
What's a Gaussian process?
So Gaussian process is basically says that it's in the Bayesian perspective. So you're assuming that your f star is sampled from some prior distribution. Okay, so you have a distribution over function space. Okay, and then you get observations with respect to this function. You get input state action pair, and you get the output spit out from this model, right? And then you can update the prior on the function to get a posterior distribution over your function, right? So imagine you have a distribution over function. So you have a distribution over function space, and then you have a prior distribution. Now you see many samples, state action next state triple samples from the ground truth model. And now you can update your belief about the function, right? So you get a posterior distribution, and then you keep doing it over and over again. Hopefully, your belief of this distribution of this function shrinks to, maybe a point mass. So that's a high level description. Okay, we are not really going to the DP side. We're going to look at the primal version of this GP formulation. So specifically, we're going to look at this formulation. Okay, so we have a feature mapping phi, and the f star can be written as this unknown weight matrix W star times this feature map phi. Okay, and phi is a feature map that maps from a state action pair to some object in a Hilbert space. Okay, so in this talk, for the purpose of simplicity, let's just think about this Hilbert space as a finite dimensional Euclidean space, okay, in RD. So basically, I have a mapping that maps from state action pair to a d-dimension object in Euclidean space. Okay, and the model f star can be written as an unknown matrix W star times this feature mapping phi. Okay, so this actually captures the sort of the infinite dimension kernel setting. So if you're familiar with kernel, so what basically this says that the inner product between the features on two pairs of state actions, right, is basically equals to the kernel between the two pairs of state action pair. Okay, but if you're not familiar with kernel, that's fine. Just think about phi as a finite dimension feature mapping. It maps a state action pair to a finite dimension vector in RD. Okay, so this transformation phi could be nonlinear. So let's look at some examples. So the first example is linear system, right? So this is a classic, linear system in LQR. Obviously I can write this in the previous KNR formulation, right? So here phi will be just a strict concatenation of state and action. Okay, and the second example is probably this piecewise hybrid linear system. Okay, so you again can write this phi using this indicator function, right? So the indicator function tells you, which piece you are in, and then you concatenate them together. So you get this phi. So this phi will be nonlinear transformation because your indicator function, your constraint might be nonlinear. Okay, so these two systems, you can write them as W star times some nonlinear transformation phi on state action pair, right? Plus additive noise. Okay, so we're gonna consider the following learning procedure, okay? Because we're assuming that F star is unknown, right? So this is all we want to try to figure out. And the learning process goes as follows. So we're gonna repeat this process many iterations. Okay, so every episode n. So this nature gonna reveals a cost function. So this cost function takes state action pair as input and spits out a scalar, a positive scalar, okay? So the learner will see the cost function, and the learner also has access to the history of the interaction between the learner and the environment, okay? And based on this history information and the cost function that she saw today, the learner will propose a new policy, pi n, from this abstracted policy class. Okay, so think about this big pi as some policy class. We will talk about some examples later. So the learner picks a policy based on history information, and then the learner tests this policy in the environment and get one trajectory. Okay, then the learner suffers the total cost, which is the sum of the cost along the trajectory measured under today's cost function that is just revealed by the nature. Okay, again, here I'm not assuming any statistical assumption on the cost function. Every day, every episode, the learner could review a different cost function, and the way that the learner chooses the cost function could be adversarial. Okay, so there is no statistical assumption on the sequence of cost functions that is picked by the learner. Picked by the nature. Okay, so what is our learning goal? So we want to minimize this regret. Okay, so let's define the objective function. So if I give you a cost function, and if I give you a policy, now the objective function of this policy is well defined, right? Which is the expected total cost if I execute this policy in the environment for h many steps. Okay, so now the regret is basically the difference between the total cost that the learner suffered across these n episodes and the minimum total cost that one would suffer in hindsight if you had access to the true model and if you had access to the sequence of cost function beforehand. Okay, so the first term is the total cost that the learner suffers. Remember, learner every day proposed a policy and she suffered that total cost, right? So after n days, this is the total cost that she suffered. Then the second term is, what if I tell you the ground truth model F star, and what if I give you the sequence of cost functions for every day, right? C1 to Cn, and what's the best thing you could do, and what's the minimum cost you could achieve, right? So this is a very reasonable benchmark. And our hope is that we can drive this regret small. In other words, we want to make this regret grow sublinearly with respect to a number of episodes. Okay, so that if you take average, you will get to converge to 0. So we will get to this point later. So again, we want to compete against a benchmark that is the minimum total cost in hindsight. Okay.
Sorry, I have a question.
Yes.
Your regret here is a function of the model as you described, right?
Yeah.
And it's also a function of the policy, right?
Yes. Yes.
So, but different models can induce different optimal policies.
Oh,
right?
The model is fixed, right? I'm always evaluating the learner's policy under the ground truth model.
But every time you may, in the algorithm, you may have multiple iterations, right? For different iterations, you may have different belief of the model. But as you said, in the Gaussian process, in each iteration, you have different belief for the model, right?
Yeah. Yeah. Okay. So yeah. So good question.
Mhm.
So there's two settings. So the first setting is the frequentist setting. Okay.
Mhm.
So this setting is that you have a ground truth model F star that is fixed.
Right.
Okay. So you believe frequentist. So you have F star is fixed. So
Mhm.
the second setting is the setting kind of what are you describing? This is the
Mhm.
Bayesian setting. So you don't believe everything is fixed. So you believe that the ground truth F star is also sampled from a prior distribution.
Right.
Okay, so in this case, the first expectation here will capture that randomness. So the expectation will be taken over with respect to the prior as well.
Okay.
But I encourage you to think about the frequentist setting where you have a ground truth F star that is fixed before the game start. Okay, it's just you don't know that.
Mhm.
Okay, so you may have a belief on it,
Mhm.
right? But the ground truth is still fixed. You know, your prior on the ground truth, you know, might be, you know, very universal, right? Very big, right? So you're
Okay.
trying to sort of get a estimation, shrinking down your prior in order to get a point mass.
Okay.
Okay, but yeah, so this framework works for both Bayesian settings and frequentist settings. But I think for simplicity, we could just think about the frequentist setting for now.
Mhm. Thanks.
Yeah, so Bayesian setting is a little bit, you know, you have to think about the prior and you have to believe, you know, every round, every day, F star is sampled from, you know, by the nature as well. Okay,
Mhm.
but this is a handleable because the first expectation will take that into consideration.
Okay.
So the first expectation is taken with respect to the randomness of everything, the randomness of the learner, the randomness of the environment, the randomness of, you know, this Bayesian prior maybe.
Okay. Thanks.
Okay. Okay, so now we're gonna dive into this algorithm. So this is an iterative model-based approach. Okay, so let's see at iteration n, we have a data set that consists of all the previous interactions that we had with the environment, the ground truth F star, okay? And we organize the data into this X prime triple, which is the state action pair and the next state resulting the given state action pair. Okay, so this is generated from the real system. And what we're gonna do is fit a model using the data set. Okay, specifically, we're gonna do this linear regression. Okay, so because we believe that the true model looks something like W star times phi, right? So that's why we're trying to learn this W hat that hopefully can mimic W star. Okay, so the regularization lambda W square, there's a missing square here, is the regularization. Okay, so I'm nothing magic here. I'm just doing linear regression, right? Because I believe that the ground truth model looks like something like W star times phi. Okay, but this is my best guess, right? But just getting a specific model is probably not super useful because I really want to get a sense of how uncertain this model is when I'm using it for testing on a different data points, you know, points that are different from the points in the data set, maybe. So I can do that by just looking into this covariance matrix. Okay, so what I'm gonna do is write out this phi transpose, this one rank matrix, right? And then sum over this one rank matrix over the data points in the data set. Okay, and then maybe you can do a PCA analysis on the data set, right? So for example, in this picture, let's assume, you know, phi is 2D. So I do PCA on my data set and I get two principal components, right? I got this the big principal component and this small principal component, right? So all this telling me is that on this big principal component, I have a lot of data, right? That's PCA tells me. And on this small principal component, I only have tiny information in the training data. I only have tiny data, right? So this really reveals some sort of uncertainty in this estimation W hat, right? So if in the test time, I get a new data point that is more aligned with this first big principal component, then I know that my model W hat will make reasonably good prediction because I've seen such kind of examples in my training data, right? On the other hand, if you get a test example that is aligned with the smaller principal component, then I know that my model prediction in that test example might be bad because I literally have very little information in the training data along that direction, along the small principal component, right? So that's all PCA tells us. You know, which direction, which subspace contains a lot of data, which subspace contains very little data. For subspace that contains very little data, we have a lot of uncertainty in estimation, in prediction. Right? So this is sort of the intuition that we want to leverage in order to build uncertainty set. Okay, so using that information, we can build the following ellipsoid ball around our estimation W hat. Okay, so picture-wise, you see this ellipsoid that is sort of rotated 90 degrees. Right? Remember, we are talking about uncertainty here. So you have bigger uncertainty in the subspace where you have little data, right? So that's why, you know, this uncertainty ball is sort of rotated 90 degrees. Right? On the direction that you have little data, now we have huge uncertainty. And what we can show is that, And what we can show is that with high probability, you know, this beta parameter is an algorithmic parameter. By setting the probability, we can show that with high probability, the ground truth model W star will fall inside this uncertainty ball. Okay, the center of this uncertainty ball is essentially our estimation W hat. Okay, so with this uncertainty set, now we can do model selection and testing. Okay, so what are we gonna do is we're trying to do this optimism in the face of our uncertainty. Okay, so we have this uncertainty set ball that contains W star, and we don't know which one is W star. Okay, so now I'm facing many choices, and I really needed to pick a model for further testing, right? So how I'm gonna do this? So I'm gonna do it in an optimistic fashion. So what I'm gonna do is look into every model in this uncertainty ellipsoid ball, and I'm gonna check what's the minimum total cost that I could achieve if the model that I'm scanning is the real model. Okay, so this is the inner mean inside this double mean formulation. And after I scan every model in the uncertainty ball, I'm gonna pick the one that achieves the smallest total cost. Okay, so I'm just trying to be optimistic. So I have, you know, for instance, I have two models, A and B. I don't know which one going to be the true model. So I'm just gonna be optimistic. I'm gonna pick a model that gives me the smallest total cost. Okay, once I pick this optimistic model, I'm gonna call this optimal control, optimal planner oracle to compute the optimal policy with respect to the sample, the picked optimistic model. And then I close the loop by executing that policy in the real environment, get new data, right? And then I repeat the same process. Okay, so in terms of how we can implement this, so remember we had this optimism step, right? This is kind of harder to implement because what we are doing is to scan every model in this uncertainty ball, right? We can't really implement that because our uncertainty ball contains infinite many models. What we can do is to turn this into a Thompson sampling procedure. Okay, so let me just describe what Thompson sampling is. So remember we had this uncertainty ball, okay? You know, we have larger uncertainty on direction on subspace where we don't have that much data, okay? And this uncertainty is captured by the inverse of the covariance matrix, right? Remember that's how we do it. We compute the PCA of the covariance matrix, and then we take the inverse of the sort of the covariance matrix in order to get this uncertainty ball. So what we can do is just treat this as a Gaussian distribution, and let's just sample models from this Gaussian distribution. Okay, again, you know, now think about this uncertainty ball, this ellipsoid ball as a Gaussian distribution. Your mean is W hat, which is the estimate that we got from linear regression, right? And we use this sigma inverse to capture sort of the covariance matrix of this uncertainty ball. So in other words, along this subspace that has large uncertainty, with high probability, I will sample a model that lives in that subspace. Right? That's great because, you know, I have large uncertainty in that subspace. I should try out models that lives in that subspace so that in the future, maybe I'm able to refine that, reduce the uncertainty in that subspace. So that's the whole intuition behind Thompson sampling. And then once we sample the model, we can just use this optimal control or planner to compute the optimal policy. And in our implementation, we use model predictive control. Specifically, we use this method called model predictive path integral. So this model MPC basically takes our model W tilde, right? The model that we guessed as input, and do optimization, roll out for 100 time steps, for instance, get an open loop sequence of controls, take the first action, execute it, and repeat the same process. Okay. So in terms of analysis, so we're gonna assume two things. So the first thing is that the ground truth model, W star, has bounded norm, Okay, so this is kind of not avoidable because even if you look into simple cases such as linear regression, right, we do need this kind of boundness assumption in order to sort of get a complexity boundness on our function approximation. So the second assumption is the regularization on my policy class. Remember, we had this abstracted policy class, right? So this assumption says that for any policy, the second moment of the total cost should be bounded. Okay, so mapping it to the simpler setting, linear quadratic regulator, this says that my policy class pi, big pi, contains all stabilizing linear control. Okay, so if you're familiar with LQR, you know, if you apply some linear control, your system might blow up, right? So this is not a stable control policy. And if you apply some linear control, your system is stabilized. And basically here we are saying that the policy class contains, you know, stabilizing control policy, right? Okay, so let's revisit the regret. So this is the quantity that we want to minimize, right? So the difference between the total cost that the learner achieved over this n days, n episodes, and the minimum total cost that you could achieve in hindsight if you had prior knowledge about the system and the cost function and everything, okay? So what we can show is that the regret scales sublinearly with respect to the number of episodes, n, right? So this is square root n. And we have this pretty tight dependency on the parameters. So here, d phi is the dimension of our feature vector phi. Okay, remember we assumed that phi lives in RD phi here, and dx is the dimension of the state space. Okay, so Vmax is the bound on the second moment, and h is the length of the episode. Okay, so in other words, if you consider the average regret, so this is what you get, right? So you get a 1 over square root of n rate, and if you take n to infinity, you get average regret approach to 0. So this is kind of nice because this says that in a long run, in hindsight, even though the learner has no knowledge about the dynamics and the cost function that the nature will review every day, she's kind of still doing as good as the best she could do if she had access to every information. Okay? And here I want to emphasize, you know, the dependency on this dimension d phi, they are basically tight. In other words, you cannot design a better algorithm that achieves better dependency on this d phi. Okay, and the dependency on n is also tight. You cannot do better than square root of n. Okay, and the dependency on h and Vmax might not be tight. Okay, so and we don't have lower bound for that yet, but d and n, they are tight. So you cannot design better algorithm to sharpen, you know, the polynomial dependency on d and n. So here we were mainly focusing on finite dimension, but remember I said that, you know, we can consider infinite dimension feature vector phi that lives in reproducing kernel Hilbert space, right? So the result is extendable to infinite dimension reproducing kernel Hilbert space using this information gain concept. Right, for those of you who know this concept called intrinsic dimension for matrix that has infinite dimension, then this is basically related to intrinsic dimension. Okay, so for matrix that has infinite dimension, there's something called intrinsic dimension that sort of captures, you know, the sort of the rank of the matrix, right? So the naive rank of infinite dimension matrix will be infinite, but if you have a matrix whose eigenvalue looks like, you know, you have two big eigenvalues and the rest eigenvalues are tiny, so then the intrinsic dimension is roughly like 2. Right, which is kind of the right quantity to capture the dimension, the rank of an infinite dimension matrix. Okay, we're not going to go into the details of this. Okay, let's look at some simulation results. And we implement this Thompson sampling plus this MPC approach, MPPI, where for this phi, we use this random Fourier feature approximation. So for those of you who do not know random Fourier feature, so basically think about this as a random procedure that takes a state action as input and outputs a high dimension vector in Euclidean space. Okay, and this is a finite approximation of RBF kernel. And we first studied from this, you know, there's a classic continuous control benchmarks people do in control literature and reinforcement literature. And this includes inverted pendulum, acrobat, swing up, catapult, mountain car example, where you need to sort of back up first and take the momentum in order to escape the valley. And this 2D manipulator where you're trying to move it around to reach a predefined goal, which is sampled freshly every episode. Okay, so we compare it to a bunch of reinforcement learning, model-based reinforcement learning baselines. So I guess the number here, it doesn't really make that much sense because I guess if you're not familiar with this environment. So what's interesting here is that this simple method, when comparing to other 10, 11 baselines that people developed in model-based reinforcement learning community, it's really doing really well, right? So here, this is arguably one of the simplest model-based reinforcement learning approach that we are using. We're not using any deep neural network. We're just using linear function approximation with random Fourier feature, basically kernels. And by just adding a little bit of exploration using Thompson sampling, and we are doing really well. And for those of you who know this model, Pirco, which uses a Gaussian process and iterative linear quadratic regulation as the optimization procedure, you can see that this Thompson sampling plus MPPI is indeed working way better than this Pirco. It is possible that we get advantage from doing this Thompson sampling for exploration, and we probably also get advantage from doing this MPC rather than this iterative linear quadratic regulator, iterative linear quadratic Gaussian, for instance. Okay, so then we look into this slightly more complicated example. Everything's still in simulation, and we looked into this contact-rich problem where our goal is to sort of pick up this ball from the table and hold it in a predefined place. Okay, so unfortunately, we cannot really make it work by using this random Fourier feature, even though we sometimes increase the dimension to be thousands, and it's still not good enough. So in other words, kernels and Gaussian processes are not rich enough to capture this contact-rich discontinuous dynamics, right? If you think about this, kind of makes sense because kernels, especially the RBF kernels, they are indefinitely differentiable. So which means that the function that you can approximate, they needs to be very smooth, right? They needs to be infinitely differentiable. But in this model, you might not be even differentiable. So what we looked into is a different design of features. So we basically say, okay, so we designed this robot arm, right? So we have a very good knowledge about this robot arm. So it looks like we don't need to learn, everything from scratch, right? So what we do is that we assume that the some parameters of the object that we are manipulating, they are unknown. For instance, the mass of this ball or the friction on this ball or the center of the mass of this ball. Maybe the ball is not symmetric, right? So these parameters are unknown. So we really want to sort of learn the dynamics when the arm is contacting with the ball, right? So what we do is that we guess these parameters based on our prior knowledge, for instance, and we uniformly sample multiple simulators. We get simulator 1, simulator 2, simulator K. And what we do is that we use the concatenation of the outputs of these K simulators as our feature function. Okay, so you take state action pair as input, each simulator outputs the next state, and then we just concatenate them together as our feature vector phi. And basically the inductive bias here is that the ground truth is some sort of linear combination of these K simulators, right? So now, of course, this is our inductive bias. We don't know if that is really true. Okay, and so basically this says that there's really no need for us to learn physics from scratch, right? We don't really need to learn everything from scratch. And we can just leverage, those simulators that we built and just learn something that is probably just unknown, such as the mass, the friction, the moments of inertia of this ball. So then we tested it on this environment, and then it actually works with just a very few trials of, manipulating the ball around a little bit, and then it quickly, successfully grasp the ball and is capable of holding it at a fixed, predefined position. Okay.
Quick detailed question.
Yes.
You're not writing simulators and stuff like that yourself, right?
No, this is a simulator called Mujalka, written by folks at UW.
Imo Todorov.
Yeah. I mean, one of the authors is his student, so that's what we used. I mean, for this problem, we also use a neural network, deep neural network. It's really not good enough to capture this like contact-rich dynamics models. So yeah. Okay. So I'm going to the last part of the talk, and if you have any questions, I'm happy to answer, before going to the last part. Okay, great. As we can see from the previous examples, simulators could be very helpful, right? So there's really no need for us to learn, for instance, gravity or F equal to ma, from scratch using deep neural network, right? You can, but whether or not we need to, that's unclear. So I think the question that we trying to look into is that, can we somehow use simulator to help, model-based learning? Okay, so this leads us to the last part of the talk. So we're gonna do policy adaptation from sim to real, with code again. For those of you to really do real robots, please don't be mad at me when I'm saying real. All I'm trying to say is that, can we sort of think about a way where we can adapt a pre-trained policy from maybe a simulation to some environment that is a little bit different from the simulator. Okay, so this is a setting. So we have a simulator and we have our favorite reinforcement learning algorithm. Okay, so let's run it for a week, several nights, and we get a really good policy about moving this robot forward in time. Okay, again, this simulator is the Mujorka simulator from Emil Todorov. Okay, so let's see, this cheetah, this half cheetah is kind of accurate, but not exactly accurate to capture the cheetah that we are interested in test time. Okay, so maybe the mass is a little bit different, the center of gravity is different, the friction is a little bit different, the size may be a little bit different. Okay, so we directly gonna transfer our policy to this real environment. Remember, we spend so much effort and time on training this policy, right? Our hope is that it can work. But with small change on the mass and the center of the gravity, it just fails, right? So the robot quickly falls down, does not even know how to recover. So directly transfer is really a bad idea. Okay, so in order to study this problem, let's write down some formulation so that we can do some math, at least at the very beginning. Okay, so again, we're gonna focus on Markov decision process. And we have two Markov decision process right now. We have a simulation, a same MDP, and a real MDP. Okay, so they share the same state space, but their action space could be different. Okay, and then their transition model could be also different. So here, Fs and Fr are basically the transition dynamics of the same and the real, which also takes state action pair as input and outputs the distribution of the next state. Okay, we consider finite horizon, and we consider a fixed cost function C in this case. Okay, so we assume that we have full control on sim. Getting a sample, getting a computation in sim is really cheap. Okay, so we just burn some electricity, and other than that, it's cheap. And you can use your favorite reinforcement learning algorithm, deep reinforcement learning algorithm, to train a policy, over many nights until you are satisfied about the performance in simulation. Okay, but in the ideal case, a sample in the real world is expensive, right? We don't want to do that many tests on the real MDP. And of course, the real MDP model, FR, is also unknown. So we really needed to learn a policy that also works well in the real environment. Okay, so that's pretty much the setting. And the assumption we're going to assume here is that the cost function this time only going to depend on the state. Okay, so this one step immediate cost. We'll look at the state and outputs a scalar. And this assumption and the assumption of the same state space basically says that a trajectory that achieves low cost in simulation also achieves low cost in real, right? It's just that we don't know how to generate such trajectory in real at this moment. We know how to generate such low cost trajectory in simulation using our optimal simulation policy, but we don't know how to get that kind of trajectory in the real because the dynamics could be different and even the action space could be different. Okay, so that's the problem we're trying to solve. But before we dive into the algorithm, so some key observation is basically the simulator and the simulation optimal policy together basically kind of tells us, what kind of state trajectories indeed have low cost. Right? Remember, both environments share the same state space, they share the same cost function that only depend on state. So a low cost trajectory in simulation implies low cost in the real as well. So we roughly know what kind of trajectories interesting trajectories that have low costs, right? And this probably implies the following, right? There's no really need for us to learn a globally accurate model, which is really hard. We don't know how to learn a globally accurate model unless you drive the robot to everywhere in the space. Okay, so in this case, maybe a local model is really good enough, right? Let's learn a local model around the optimal trajectory that achieves low cost. And then we know what this low cost trajectory looks like by examining our optimal simulation policy in simulator. Right, so that's really the key observations. And let's design this closed loop control policy. So we're gonna do model-based learning. Sorry. So let's assume that we have some learned model f hat that ideally is approximating the ground truth transition dynamics of the real. Okay, and let's design the following closed loop policy control. At every state x, this closed loop policy is picking an action such that the predicted next state from my predictor f hat looks very similar to the next state that would be generated from the simulator by executing the optimal simulation policy. Okay, so we're trying to select action such that the next state from our predictor match to the next state from the simulator with the optimal simulation policy. Right, so the intuition is that the optimal simulation policy is doing really well inside the simulator. So let's try to pick action in real so that the next state is mimicking the state that is generated in the simulator by the optimal simulation policy. So that's the whole intuition. And you can treat this policy as sort of MPC policy with just one step look ahead.
This is an assumption, right?
No, this is my design.
No, but that you say you have the wrong model. You find the optimal policy for the wrong model. That gives you a trajectory in the state space. Yeah. And then you're assuming that with the correct model, you want to have the same trajectory in state space.
Yeah, yeah.
But that's not, do you think that's a common thing, or is it just a guess, or
No. This is the ideal thing that I want to achieve, right? Imagine my f hat is equal to fr. Then this is a reasonable thing to do.
Yeah, but on the way, it might not be a reasonable thing.
Yeah, exactly. Yeah, so we will get to the algorithm in the next slide. So here I'm just defining the closed loop policy given a learned predictor. Okay, as you said, the learned predictor could be very bad at the very beginning. My policy might be doing bad things, but I'm gonna keep refining my policy. I'm gonna keep refining my model.
And your policy.
And my policy, yeah.
And your policy is going to chase the trajectory that you already know optimizes the bad model.
Yes.
In the end, everything will be right. Okay.
At the end, it will converge. Well, under some assumptions. We will get there. Yeah. Okay, so the question is, as you said, how we can learn this model f hat in a reasonably good, fast way. Okay, so here is the algorithm. We call it policy adaptation with data aggregation, in short, PANDA. And it's an iterative refinement model. So at iteration n, I have this model f hat. And I'm going to define the same control policy, this one-step MPC look ahead, right? This is a policy that we talked about before. And again, I want to emphasize, inside this simulator, we use the optimal simulation policy, right? We're trying to chasing the trajectory generated by the optimal simulation policy. And we're going to test this one-step MPC policy in the real environment to get new data set. We just want to see how good it is, right? Is it really matching, the simulation trajectory? So we get new data set in the form of state action X state triple. And we do data aggregation. We combine this new data that we generate in this episode with all the previous data. Okay, so now I have a new data set. What I'm going to do is refine the model. I'm going to train the model using our favorite supervised learning technique, maybe maximum likelihood estimation. Okay, so I'm going to pick a model from my model class that achieves the maximum likelihood of fitting this entire data set. Okay, so my hope is that the model is slightly better than the previous model because now I get new data in this episode, and then I close the loop. Okay, so now gets to the assumptions that we need in order to analyze. Okay, so I think the first assumption is really necessary in order to guarantee successful adaptation. Okay, so the equation looks like complicated, but let's just break it down to this cartoon image. All it's saying is that at state X, if I take action A in the simulation, I get to X prime, then there must exist an action A prime in the real environment's action set, such that if I take A prime at a state X, I get to the same state X prime. Okay, so this is what we call adaptability. This is an assumption. So this saying that ideally this is adaptable, even though I need to take a widely different action in the real environment, maybe in order to match to the simulation. So this knowledge is unknown and the learner needs to figure it out, right? But at least there exists one so that it's adaptable, it's hopeful. And the realizability assumption, which is my model class, my neural network model class, for instance, is rich enough to contain one neural network function that can approximate the real dynamics reasonably well. Okay, so this is the guarantee, informal guarantee we get. After you run this algorithm n iterations, you really get a policy whose trajectory in the real environment looks very similar to the simulated trajectory that's generated by the simulation policy. Okay, the first term is a trajectory distribution of the learner policy pi hat in the real environment. And the second term is a trajectory distribution of the optimal simulation policy in the simulation. And we know that the optimal simulation policy generates low-cost trajectories, right? So if the distribution, if the total variation distance between these two distributions approach to 0 as n approach to 0 in the rate of 1 over square root of n, then we know that at the end of the day, the learner policy will achieve low cost in the real environment as well. Okay, so let's look at some simulated results. So this is the result in the simulation. Okay, so we changed the mass in this case and moved the center of gravity a little bit forward. So the robot probably would just fall down if you apply the same policy. But after this adaptation, we were able to move this robot, this slightly changed robot, forward in time in a reasonable speed as well. As you can see, this is not as stable as the policy in the simulator. Sometimes the robot tends to fall down, but it quickly learns how to recover from the motion. Okay? And in terms of comparing to popular deep reinforcement learning methods, I think this is kind of interesting. So this is the performance of our algorithm. So here, let me explain some components. So the y-axis is the reward. So here, again, apologize for overloading reward and cost. Here we are maximizing reward. Okay, so the x-axis is the number of time steps you use in the real environment. Okay, so the red curve is our approach. So the green curve is something called domain randomization. I think for those of you who know robust control, what domain randomization essentially is doing is basically generate many simulators and trying to find a policy that simultaneously maximize all the simulators so that you can hope, adaptation when you transfer this learner policy to the test environment, right? This is a common approach people use in robust control, but somehow deep reinforcement learning people call it domain randomization. Doesn't matter, whatever. The third approach is model-free reinforcement learning, deep reinforcement learning methods, PPO, directly running on the real environment. So you ignore the simulation, you just apply your favorite model-free reinforcement learning algorithm inside the real environment. Of course, it will be very slow. And the third one is kind of complicated, which is this model imitation learning with generative adversarial stuff. It sounds very fancy, but doesn't really work that well. Okay, so as we can see, the Panda is learning much faster in terms of using number of samples from the real. And the another baseline is that what if we run this, our favorite model?
So you have a red curve and a blue curve. Both of those are Panda?
Yeah, both are Panda. And the blue curve is fitting a parameterized neural network policy to mimic the one-step MPC policy. So the MPC policy might be slow, right? Because we want to optimize selecting this action. So you might have to do this cross-entropy methods in order to select this action. So what the parameterized policy basically does is that I'm trying to fit another neural network to mimic this one-step MPC policy. Okay, but they achieve similar performance. And in terms of computation, real-time execution, this parameterized policy is faster, for sure. Okay, so one last baseline that we want to compare is that what if we run this, our favorite model-free reinforcement learning algorithm, PPO, using deep neural network on this real environment until its convergence, maybe after millions of real world samples, right? So the top dot curve is the curve you get upon convergence of PPO. So as we can see, we really sort of very sample efficient. As you can see, even around 5,000 samples, we were able to get a performance that is almost half of the optimal one that you could get if you run your favorite deep reinforcement learning algorithm overnight, after million steps. So this basically gets to a conclusion. So in this talk, we sort of started from information theoretical consideration of model-based learning. So we talked about, this exponential separation between model-based learning and model-free learning. But unfortunately, the algorithm there is not computation efficient. Then what we said is that, let's take one step back. Let's look at a more refined, most restrictive model class, which is called a kernelized nonlinear regulator. And we analyzed an algorithm that uses Thompson sampling plus traditional model predictive control, which is the MPPI framework developed from people at Georgia Tech. And lastly, we look into this potential approach for policy adaptation from sim to sort of real. And we basically say that with the help of a simulator, we can really sort of reduce down the samples that we need in the real environment in order to learn something reasonably good. Okay, so that's it. Thanks, everyone. Happy to take any questions.
Okay, I have a question on part 2.
Yeah.
About the planning horizon.
Okay.
Yes, in the first part, you gave some examples like race car and computer games, right?
Yeah.
The planning problems they are supposed to solve are primarily finite horizon, right? But the planning steps, the planning horizon can change, right? But your method RC cubed only can solve the model for one fixed horizon, which is H, right? How do you adapt H for the fixed horizon for like various kind of problems? And one benchmark example you give is inverted pendulum, right? And that is an infinite horizon problem, right? Then how do you handle that problem?
Yeah, so basically, for this infinite horizon problem, you might quickly converge to a stationary policy, right? So if you set H to be long enough, capital H to be long enough, you basically, after 100 steps, you already converge to a stationary policy that can always just, maintain the pendulum at the upstream position. Right. And again, we are running MPC, right? So you're looking ahead. You're based on where you are. You're looking ahead for instance, 100 time step, and you execute the action in the open loop sequence of actions, and you repeat the same process, right? We keep running this closed loop open loop, closed loop MPC policy. Okay. And another way to adapt it is that it's common in reinforcement learning. You introduce this discount factor.
Discount factor. Okay.
Yeah. That's all they do, in these video games where you may have super long and different kind of horizons, right? Based on, how you are playing. Yeah.
I see. Okay. And another quick question. You use MPC as a planner, right? Did you try use other method like dynamic programming?
No, we didn't. Ideally we could. I did suggest to use this differential dynamic programming as a subroutine for sort of like one step in MPC. It work as well as this like random shooting based method MPPI. Okay. So MPPI is very simple. Like it's out trajectories and weighting them exponentially based on the cost function, and then you just average them together based on the weighting. And it sounds like a very stupid algorithm, but it indeed works well in these benchmarks, and it's very parallelizable, right? Because the shooting can just be done, and shooting and validation can just be done in parallel for long horizon. Yeah, in principle, you can do differential dynamic programming.
MPC is scalable to long horizon problems.
Yeah.
Yeah, thank you.
Thanks.
I have probably 10 million questions, so I should probably talk to you some other time. But you have a sim to real, but it still seemed like your real, you had to do world. So
Yeah,
so you're I mean you're trying to model sim to real by sim to sim, and but your the thing you call real is something you had to evaluate. It looked like thousands of times, and for lots of robots, you can probably you can maybe do 10 times. You can't do 10,000 times.
Yes.
And so usually when I think about the sim to real, at the sim to real at the
Hey, Andy, you're muted. But also, I just need to interject quickly. We are technically over time, so the recording will stop here, but you can stay and ask questions. I'll leave the room open. I'll be here.
okay, sorry. When I picked up my hand, it took